Good afternoon. I'm Julius, and I'm presenting on prediction in rural electrification. Please. And so, electrical energy is fundamental to socioeconomic and techno-economic development, and it links to several sustainable development goals like no poverty, quality education, and gender equality. But then, not everyone have access to electricity. If you look at it from the global level, um, electricity access improved by 4%, in the year 2015 to 2021. And then it was projected that 675 million people will still lack access to electricity by 2030, as said by the World Bank. If you narrow down to sub-Saharan Africa, we have 31% of the rural population having access to electricity, leaving 69% without it. And then if you come down to Ghana, we have 75% of electrification at the urban center. And then we have 95. And then in the rural center, we have 74% of the rural electrification, leaving 26 of the rural communities without power. Now, the problem is that it's very difficult extending the national grid to these remote areas because some of these communities are on islands. And because of the sparsity of their settlement and the population size, so it is not economically viable to extend these national grids to the place. And so one promising solution to solve that problem is the implementation of mini grid system. And when I say mini grid system, it's the combination of solar panels, convectors, batteries to provide light for this group of people. But then to size the system for this group, we need to know the consumption of the people. But these people don't use light. So how do we then get the energy patterns to size the system? Again, the existing models also do not have or lack the interplay between the population growth, the household connections, and the appliances growth. And so this project actually sought to develop a stochastic based deep learning to better predict the electricity demand in rural electrification. And so we came up with a stochastic model, and that links the population growth, the household connections, and then the appliances growth with some parameters to also account for the randomness. If population increases, what is its effect on consumption? And if the household, we have a lot of houses connecting to the mini grid, what is its effect on the power consumption as well as the appliances? And we did some sensitivity analysis on it. And afterwards, we came up with some load profile. We combined it with some existing data from other communities. And then we created several features out of it, fed it into a deep learning model. And so we ended up with these results. We also went further to perform some experimental settings on the maximum peak, comparing the measured data and then the load profile, looking at the error margin between them. And so we could see the prediction over here, very well predicted. It could explain a lot of variables in the models. Then we look at comparing the load profile with the existing historical data to see how best the model is able to predict for an unelectrified area. And so, in conclusion, we were able to come up with a framework that actually minimizes the prediction error in rural electrification demand. And as part of this model can also contribute to policy, coming up with a very good policy in terms of planning mini grid system. And as part of future research, we also admonish that, we could integrate socioeconomic and environmental variables to also better refine the model. Thank you.